Awesome. So welcome to another series of the NL seminar. I'm your new host now after taking over from Miriam. Today we have Jason Wei, a senior research scientist from Google Brain. He his work on large language models. He's mostly famous for the chain of thought prompting and also instruction fine-tuning and also analyzing emergent abilities in large language models. His work has been featured in a lot of Google AI blog posts, where the chain of thought prompting was actually presented last year during the Google I/Os event by Google CEO Sundar Pichai himself. Before Google, Jason was at Dartmouth College. I had a pleasure to meet Jason in person a couple of times during the CMU Open House and also USC's Open House a couple of years back. And it's great to have him join us back for a talk. So Jason, thank you. Take it away.
Yeah, let me try to fix my screen sharing. Okay. Great. Yeah, thanks for having me, Justin, and thanks everyone for coming. Today I will talk about emergent abilities in large language models. Okay. So here's a short outline of the talk. So the main framing of the talk is going to be around emergent abilities of large language models, which are these abilities that you can observe in small models, and you can only observe them in large models. And there's going to be a little sub-result on how inverse scaling can become U-shaped, which is another type of emergence. And then I'll also talk a bit about chain of thought prompting and specifically these three papers below. Yeah, as I think Justin said, if you have any questions, feel free to just interrupt me during the talk. So this is the first paper I'll talk about, which was published in TMLR last year. And this was a bit of a mix between a survey paper and a position paper. And it was a collaboration among a bunch of groups, not just at Google, but also DeepMind, UNC, and Stanford. So the context for this paper is that for several years now, we've observed in language models that there's a clear and predictable relationship between scale of the model and downstream performance. So here's the sort of canonical plot from Kaplan et al., which basically says that there's a power law relationship between the test loss on some test set and then three axes of scaling. So compute, the data set size, and the number of parameters. And if you look at the x-axes on these plots, you can sort of see that this trend covers several orders of magnitude in terms of compute, which means that if you continue scaling the test loss, you would expect it to continue decreasing. So it's sort of predictable in that sense. While that's sort of a predictable phenomena, there are other tasks which I think are really interesting where the performance does not appear to continuously improve as a function of scale. And the performance of those tasks cannot be predicted ahead of time. So to zoom out a bit, emergence has been a phenomenon that's been seen throughout science. And this idea was probably popularized in 1972 by Philip Anderson, who's this Nobel Prize winning physicist, in this paper in Science called More is Different. And I think one of the easy ways that I like to use to describe it is that emergence is a qualitative change that arises from quantitative changes. And here are some examples from Jacob Steindart's blog post where he says, for example, with the bit of uranium, nothing special happens. With a large amount of uranium packed densely enough, you get a nuclear reaction. Or given only small molecules such as calcium, you can't meaningfully encode useful information, but given larger molecules such as DNA, you can encode a genome. So in this paper, we'll focus on emergent abilities with respect to large language models. And there's this natural question of like, so the definition is ability is emergent if it is not present in smaller models, but it is present in larger models. And then there's sort of this natural question of how do you precisely define like smaller models versus larger models? And this question is a bit complicated because when you scale up models, often a lot of things change. And it's really a function of like different things. But one way of looking at it is among the sort of three axes that language models have traditionally been scaled by. So training flops, number of model parameters, and the training data set size. And we're going to focus mainly on training flops and number of model parameters. Traditionally, for most models, except for Chinchilla, these things are scaled at the same time. So like as you increase the model parameters, the amount of training flops you need increases. Training data set size is sort of a third axis, but for most model families, each size model is sort of trained on the same data set. So the data set is often constant. So the first type of emergence that I'm going to talk about is emergence in the few-shot prompted setting. And if you're not familiar with how the few-shot prompted setting works, feel free to ask. But basically, language models are like these really good next word predictors. And the way that we typically prompt it is by appending a few examples of an input-output pair. This example for sentiment analysis and movie review and the sentiment. And then we ask language model to predict the next word as for the target. And the sort of definition that we use for emergence in this few-shot prompted setting is that a few-shot prompted task is emergent if it achieves random accuracy for small models and above random accuracy for large models. So here's 8 examples of emergent abilities in this few-shot prompted setting across a range of different language models. So the way to sort of read this is each of these different plots, each of these 8 plots is a different NLP task. And the x-axis is model scale. So here we use training flops, but it will look similar with model parameters. And then the y-axis is the accuracy on a particular task. And each point is a different model with different size and training flops. So it's not intermediate checkpoints of the same model. Each point is a different model. And we have different models from Google, DeepMind, OpenAI, and also random performance shown as a pink line. And what you can see in each of these plots is that the performance of the language models is about random for a bunch of small model sizes. And then when you scale to a large enough model, the accuracy suddenly spikes to well above random. And the interesting thing about this is that if you were to just look at the small model sizes, you might predict that if you would continue scaling, you never get above random accuracy. But indeed, when you continue scaling, there's sort of this point where you suddenly start to get much better than random accuracy. And to be a bit more concrete about like what types of tasks are emergent, here are just a few examples. So here is the multitask NLU or MMLU task. And this is basically a compilation of like high school to professional level exams. And the question shown here is a high school math task, I believe. And basically the model is given a few demonstrations and it has to pick the answer from 4 options. And as you can see from the 3 models shown here, the performance only becomes random if the model is trained with something like 10 to the 24 training flops. Here's another example from the Big Bench benchmark. If you're not familiar with Big Bench, it's basically this benchmark of 200 crowdsourced NLP tasks. And here's just one example. So in this task, the model takes a input sentence and has to give the International Phonetic Alphabet or IPA transliteration. And here, the performance is measured in blue, which is an n-gram matching metric. And you can see that you have to get past 10 to the 22 flops, basically in order to get better than random performance on this task. Another interesting result that I want to talk about is from a separate tech report that we put out recently. And so as some context, there's basically this inverse scaling prize where people try to come up with benchmarks for which model performance would actually get worse with scale. And you would call this like inverse scaling. So some of the tasks will end up being like this one. Like repeat my sentences back to me. Input, all that glisters is not glib. Output, all that glisters is not. And then the model has to output glib. So small models actually end up getting 100% on this task because they don't know the quote, all that glisters is not gold. So they're pretty good at just repeating glib. And then if you take a medium-sized language model, you can see that the performance actually decreases because all that because the medium-sized language model knows the quote, all that glisters is not gold. So it says gold and that hurts the performance. And what we argued in this paper is that if you just continue scaling up the language model beyond the size where it decreased a little bit, the performance might actually go back up after it goes down. So in this case, the large language model knows the quote, all that glisters is not gold, but it can also understand the instruction of repeat my sentences back to me. So it successfully replies with glib. And basically the point is that just because model performance decreases for a given task with respect to scale for some model sizes, doesn't mean that it can't go back up again if you keep increasing the model size. And this is sort of another type of emergence. In addition to few-shot prompting techniques, where specific like NLP tasks are given to the model in this few-shot manner, there's a second type of emergence that we talk about in the paper. And we call this type of emergence emergent prompting techniques. And the definition here is that a prompting technique is emergent if it hurts performance compared to some baseline for small models, and it improves performance respect to the baseline for large models. So the example here is a technique called RLHF. It's used widely by OpenAI and Anthropic and is likely used in ChatGPT. And it's basically fine-tuning the language model using reinforcement learning on preference data that's labeled by humans. And what the plot here is showing is, again, the x-axis is the number of parameters in the language model. And then the y-axis is the mean evaluation accuracy on a set of zero-shot tasks. So these are like NLP tasks that were not included as part of the RLHF training. And what you can see is that for small models, if you do RLHF, it actually hurts the performance on these zero-shot NLP tasks. So the orange line is below the blue line. And then for large models, you see a positive delta.
Hey, Jason, one clarification here.
Yes.
Can you hear me? Okay. Yeah. So how is it related to prompting? How is this RLHF related to prompting here?
Oh, I guess it's just vaguely related, but it's a fine-tuning stage where you can change the type of prompting where you can sort of phrase the zero-shot task as an instruction. But I'll talk about another, I guess, more formally prompting technique.
Okay. Thank you.
Yeah. Yep, great. So here's the sort of hand wavy diagram that I like to show. Oh, yeah, I guess I should mention. Yeah. So later I'll talk about chain of thought prompting as another emergent prompting technique, and we'll go pretty detailed in that. So here is a hand wavy diagram that I like to use to sort of visualize like this framework of emergence. So on the x-axis is sort of the scale of the language model, and it doesn't really matter what the numbers are right now. And then on the y-axis is this like range of things that language models can do. And the blue curve basically sort of says that as you increase the size of the language model, the range of tasks that the language model can do sort of gets larger, And then there are sort of these emergent abilities where you can only observe them in models above some scale, and for models below that scale, you can't find that ability. So I wanted to also have a couple of slides to provide a bit of nuance for this emergence framework, where although scaling is one of the main ways that we've seen emergence, there are a lot of other factors other than simply the scale of the language model that go into like these new techniques. Yeah, I can answer Daniel's question. The question is there intuition on why RLHF hurts performance on smaller models? My sort of thought on this is that, like, for smaller models, you have this limited capacity, and maybe you're using up all the capacity just to learn the RLHF, fine-tuning data. And it's not particular to RLHF. There are also similar results with supervised fine-tuning. But basically, for small models, uh, one hypothesis, and I don't have concrete evidence for this, is that you might use up all your model capacity to learn that data, and then on unseen zero-shot tasks, you would do worse than before. For large models, you have this additional capacity where you can use some of the like you both learn how to express what you know better through this RLHF or instruction fine-tuning. And then you still have enough parameters to like keep all the world knowledge that you knew before. And you can better express that in a zero-shot manner after doing this RLHF or instruction fine-tuning. Good question. I don't have evidence, but that's just a hypothesis that I have. Okay, so yeah, basically what the slide is about is that smaller models with better data can also lead to emergence, even when larger models trained on worse data don't demonstrate worse behavior. So here is an example from a plot from Big Bench. And you can see that the performance actually doesn't emerge for language models here, such as Lambda and GPT-3, up to 175 billion parameters in the orange. But for Palm, 62 billion, which is actually smaller and uses less compute than Lambda, I believe. We actually do get this emergent behavior where it does a lot better than random. And we don't know for sure why, but I think one running hypothesis is that the data for Palm is generally higher quality, which means that if you train on this higher quality data, then you can unlock emergence without increasing scale or compute. And this is a bit hand wavy about what better data means, and sort of the reason is that it's pretty hard to both characterize the quality of the data and also to do like these ablations on large scale models for data. So here's to make that a little bit more concrete. Here's sort of a smaller scale experiment that shows the importance of data. So basically what's happening here is that we have this toy task of subject-verb agreement, where the language model has to use the singular form of a verb for singular subjects, and also the plural form of the verb for plural subjects. This is like a very simple English grammatical rule. And then these are like BERT-based models. And we basically redid the pre-training for them, where we varied the frequency of certain target verbs in the training set. And what you can see in the plot is on the x-axis, as you increase the frequency of the verb in the training set, the error rate will go down. And the point is basically here that if you hold compute model parameters and data set size the same, but you have a data that's more in domain for the evaluation benchmark, then you can get a much better performance just by having this sort of data that's closer to the evaluation benchmark. Another sort of important thing to note about emergence is that, like, if you're especially interested in like some particular task, like instruction following, you can actually enable that in smaller models with the sort of further step of fine tuning. So emergence is not to say that you will never get some behavior that you see in a large model in a smaller model. So this is the RLHF method again. And you can see that if you do RLHF on small models at the 1.3 billion parameter size, then you can actually beat the performance of larger models without this RLHF. And the point is that like when we do scaling, we might discover these sort of emergent or new abilities that become popularized. And if the ability is super important, then you can improve the performance of that ability on smaller models with this targeted fine tuning without having to scale up as much. Another important point in this framework for emergence is like, which metric do you use as the x-axis for looking at emergence? And so far, we've mostly focused on number of parameters or the amount of compute as the x-axis, but there's this other perspective which a lot of people from DeepMind have, and I think this is a pretty valid way of looking at it, where the scale of the model is really just a proxy for like how good the model is in terms of general perplexity. So you can take the perplexity on like some dev sets, such as Wikitext, like 103, which is basically the subset of Wikipedia. And then you can use like the perplexity as the x-axis to measure emergence as well. So on like the right bottom plot there, you can see that we can plot emergence also with respect to Wikitext perplexity as the x-axis. And you get a similar plot where like you'd see this emergent behavior, where as you go down past a certain perplexity, you suddenly get much better performance on MMLU. And the reason to sort of add perplexity as one more way of looking at it is that right now there's this like pretty strong correlation between model scan perplexity. If you look at the top middle plot, you can see that, like, for example, as you increase training flops, the Wikitext perplexity is like pretty predictable. But the point is basically maybe in the future with better data and better architecture, we'll have smaller models train on a lot fewer flops that will just have much better perplexity, and maybe in the long term, the perplexity could be a better way of measuring the scale of the model. A better way of looking at emergence.
Do you think it's question?
Yeah.
Do you think it's perplexity, or is it perplexity on wiki? Because one way to think about perplexity on wiki is ability to learn encyclopedic content. So would you expect to see the same thing if you ran perplexity on, I don't know, all the screenplays, all the scenarios for the Big Bang Theory, for example?
Yeah, that's a good question. Maybe. I think one of the really challenging things, and the reason why we didn't frame the entire paper on perplexity is that you sort of, all these models are trained by like different companies or institutions on different data sets, and there's no way to sort of hold out a certain subset systematically across all of the different models that were trained. And you also might do a lot better perplexity on I forget what your example is, if you just happen to have like a slice of data that was like a lot closer to that type of evaluation data that you're measuring your perplexity on. So like in this plot, we really only had Gopher and Chinchilla because they were sort of both trained by DeepMind, and they were able to like systematically hold out a test set to evaluate perplexity. But yeah, I definitely think like there's this like pretty unclear question of like, if you want to use perplexity as the lens for view emergence, how do you choose what data set to use, and how do you like control that across different models? So yeah, I agree. It's pretty unclear like how to do it systematically for perplexity. Okay, so this last slide is something that I think is super exciting about scaling, is that like you could basically in some tasks beat prior like task specific state of the art just by scaling up the model more. So in these plots we have this like prior soda as this dotted line. And this is fine-tuned usually on thousands of examples. And what you can see is that, in these plots, the performance is not necessarily emergence by the definition of being random for small models and non-random for large models. And here it actually improves pretty predictably for the model sizes shown. But this is kind of a sort of sociological type of emergence in the community where like you can see sort of a shift in the mindset where if you wanted to get the best performance on a particular task, the way to do it might be to scale up the model and then do a few shot prompting instead of the old paradigm of collecting a large fine-tuning data set and then fine-tuning the model for the particular task. Obviously, it's not like super compute friendly to do this for every task. But I think that the fact that you could get SOTA on a task without specifically training for it was a pretty compelling message for a lot of people.
Jason, do you think there's still room for fine-tuning these models, like basically doing the pre-train fine-tune process for the large language models, and then if you're able to exceed even further on top of that? I'm just wondering if the generalizability is definitely the more helpful signal here, and then you don't want to actually fine-tune. Curious.
Yeah, good question. I think there's like a couple of like things that like are pretty challenging about fine-tuning like a huge model. So for example, if your model's like 540 billion parameters, and then let's say you want to fine-tune it on like a single task, maybe there's this like premise of like, why do you want such a large model just to do a single task? Like a large model has a lot of parameters and you probably want it to be multitask. The other thing is that like if your training data set is small, it's pretty challenging to do like controlled experiments where you might want to pick the best hyperparameters for a 540 billion parameter model, but the fine-tuning itself is like so expensive that you can't do like a valid hyperparameter search, and maybe it overfits a lot on your particular data set. And it's hard to measure whether, if you scale to like a relatively large scale, are you actually doing justice to like a, like a reasonable fine tuning, or are you just doing so poorly because like the fine tuning behavior of those models are so poorly understood?
When you say sociological change, are you saying that you are seeing less desire to collect training data now?
Yeah, I think one of the things that I really am excited about for these large language models is that like because you only need these like few shot prompts that even one person could write by themselves, and you can get like a decent performance on a lot of tasks. This sort of lowers the barrier of entry for like non language people to use language models for their particular task. And before you need like thousands of examples to fine tune T5 or whatever, but now people from like robotics, for example, can use large language models as part of their research, and I think that's really exciting.
I mean, I would say it maybe lowers that bar, but it raises a different bar, which is that you're now constrained to people who can have access to 100 billion, or in some cases 540 billion parameter language model, which is a pretty small subset of all the people that want to do machine learning. And then on top of that, I guess I want to editorialize and say that once you've collected training data, there are many ways it can be used that are potentially not anticipated by the collectors. And I'm skeptical that the same is going to be true for these models. And I wonder what you think about that.
Yeah, I think one of the cool things is that like I tend to take like a longer range view of AI, like in the range of decades. And if you sort of look at like what the community has access to back to this state of the art, I think the lag time relatively is like a bit shorter. So like you could see like there's some open source models that are sort of beating 62 billion parameter models or models that are like 10x larger. For example, T0 beats GPT-3 on a lot of tasks. And so I think increasingly there's like more open source models that are available to the community for use. And I think that's that's in the right direction, although it's not perfectly, yeah, not everyone has access, which isn't perfect. I forgot the second part of your question. Maybe it was like you have these unintentional.
No, the second part was that there's it seems to me that there's value in data collection that is more than just for the task of intention, right? Like, so the you know, the Penn Tree Bank, for example, had, you know, was from 1990 originally, right? And had many years of use and repurposing, and there were lots of things that were potentially unanticipated by the creators at the time. And of course, you can few shot prompt a model different ways, but a purpose-built model to do a thing, right, is going to do that thing. And you know, you also have to. I have yet to see an actual like binary that lasts for 20, 30 years, whereas a corpus certainly does. And I wonder about the sociological change having a negative impact on research, because you just will be building fewer and fewer actually reusable resources. So the point is that data has its own inherent value, and I'm worried that you're actively encouraging less collection of data.
Well, I think data is sort of a barrier of entry for some people, and there's nothing stopping, you know, researchers who are interested in collecting more data if they want. So I think if people see the, and also you have to, like for these evaluation sets, you have to collect a lot of data usually. So I don't see that as directly being in conflict. But yeah, maybe if you feel, if I'm missing something, I would be happy to talk about it after the talk as well. Okay, great. So in summary, I think emergent abilities are sort of this pretty special phenomenon in language models, where you can observe them by scaling, and they're sort of only observed in large models. And what I think is super interesting about them is that if you just looked at the scaling plots for small models, right, you wouldn't be able to predict that you would get them by scaling up the model. And here's a sort of couple of reflection points I wanted to briefly talk about. And the first is that emergence is really a framing for like viewing the language model space, at least for me. And you can see it as sort of an implicit argument for why we should keep scaling, because these abilities are sort of hard to find otherwise. And even especially just a year ago, I think a lot of people didn't believe in scaling. So this framework of thinking is I think pretty important. The second point that I've realized is that if you work in industry, at least, there's this kind of tension between emergence and production tasks. So emergence is sort of this task general phenomenon where you have a huge model that can perform any task. And then on the other hand, you have these production tasks, for example, say Google Translate to Spanish, where you probably don't want to have a huge model that does everything. And instead you want to like fine tune a specific model. You have a lot of data to do it, and you want to serve that model at low cost.
Jason, one question. So, sorry to interrupt that, but I'm assuming that there are some tasks where emergence doesn't happen and some tasks where it does. So is there, where are we on getting a sense of what kind of tasks do we see emergence? Because that understanding can make it more useful moving forward.
Yeah, that's a great question. I can pull up a little plot that we have that isn't great, but I think it's tough to sort of get a good characterization of tasks. Let me find a task. So let me share this tab. Okay, am I sharing like a little chart here? So basically there's like 200 tasks here. And then we can manually classify them as like emergent, you know, with Lambda / GPT, or emergent with Palm. And then you can also classify them as like either smoothly increasing or like flat. And you can see that, like, okay, if you sort of rank them by like number of tasks, you can see like a lot of emergent tasks have like these are different tags that are added by like people who added tasks on Big Bench. So it's not like a perfect categorization, but you could see like these are sort of types of tasks that are like emergent or like non-emergent. And then you can also see like in the pink, flat means that like no model is doing better than random. So like basically no model can do these tasks yet. And you can also see like what types of tasks that models are struggling on. Maybe this isn't super helpful, but like this is like maybe initial attempt on like how to be more specific about what types of tasks are emergent. But yeah, I think this is something that people would benefit a lot from if we were able to do a better characterization of tasks. Is this helpful?
Thank you.
Okay. Great. So yeah, and then the last point is that I think there's this like super open question of like why emergence happens and how we can predict it for a given task. And I haven't seen too much work on doing this, and so maybe it's too hard, but I definitely think it's a direction that is worth spending some time on. And so the second part of this this talk, I'll go into one specific emergent ability, which is called chain of thought prompting, and this basically enables language models to do multi-step reasoning tasks. And I'm super excited about the work around reasoning done in our group and also elsewhere, and it was cool to see Sundar present this at our Google I/O Press event. So the motivation for chain of thought is that we basically want to enable language models to do more complicated tasks. And the way that we do this is to basically guide them with metadata, for example, a reasoning process, if we want them to do a multi-step reasoning task. So you can see in this figure, so in standard prompting, basically, you would just give the input question about a simple math question, and then you give the final answer. The answer is 11, and then you have a new question, and then the model unfortunately gets that wrong. And what we do in chain of thought prompting is this very simple modification where instead of just having question answer pairs, we will add a intermediate thought process into the prompt. For example, here we add like Roger started with 5 balls, 2 cans of 3 tennis balls is 6 tennis balls, 5 plus 6 is 11. And we do this before giving the final answer. And then for an unseen question, the model will be able to generate a new chain of thought before giving the final answer. And this enables it to get this particular question correct. And here the prompts are manually composed. And so I basically just wrote these chain of thought prompts in the exemplars. And prompt engineering can help to some degree here. Just to be a little bit more concrete, so here is a little demo. So am I sharing this? Okay. So here's like a typical prompt. So you have like, a question and then the final answer, question and then the final answer, and then question and then the final answer. Then you have your like test time question. And if you just do this, unfortunately, the model gets it wrong. And then if you do the chain of thought, it's exactly the same prompt with one modification. Before giving the final answer, we add this chain of thought as part of the prompt. So here we are. And then at test time, we can ask the model, and then the model will generate this chain of thought. Cafeteria had 23 apples originally. They used 20 to make lunch. They had 23 minus 20 equals 3. They bought 6 more apples, and they have 3 plus 6 equals 9. The answer is 9. So that enables it to get this math problem correct. And then we can look at like an even easier case where the task is basically to take the last letters in the words Bill Gates and concatenate them. So the answer is L from Bill and then S from Gates. And if you do this, the model gets it wrong for Elon Musk. But if you do chain of thought, you can see that this is basically trivial. So, it says the last letter of Bill is L, last letter of Gates is S, the answer is LS. And then we can do the same thing for Elon Musk, and then it gets this one correct. So it says NK. Any questions on how that works? I don't want to move forward. If people have questions, I should clarify before moving forward.
One question here. I mean, it's definitely looks like the chain of thought prompting would gave more supervision, right? That
Yep.
hey, this is how you get the last letter for a word. And what if we just add that? Let's try. Is this live? Can we try this right now? Or
Yeah, sure.
so maybe. Yeah, so I mean, what if like giving supervision about that? Hey, the last letter of a word can be is the or like telling that separately rather than a chain of thought. Ultimately, the objective is to give more supervision, right? Is that
Yep.
I mean, and that might in itself lead to good performance. I'm not sure.
Yeah.
Yeah.
Are you saying that like maybe if you just gave the information separately, like these are some examples of what last letter is,
yes,
and then you said, and then you ask the question, take the last letter of the words and put them together.
Because by giving this prompt, we gave more supervision, right? In that
two instances of supervision.
Yeah, so may not be a fair comparison. Yeah. Also, I think did this work also involve adding to the prompt the thing step by step? Or was it this work or?
You can do that, but
help?
we didn't do it in this work.
Okay.
The thing that I think to know about that trick is that it often doesn't work if you don't have an instruction fine-tuned model. And the second thing is that it often only works for tasks like math word problems where you've seen a lot of similar data in the training set.
Okay.
What if you have like faulty reasoning in the chain of thought? Like if for example, the example was like the last letter that Bill sent was L. The last letter that Gates sent was S, which is nonsensical, and it's maybe referring to post whatever. You could just say something that's just not
accurate,
but gets the right answer.
Yeah.
Does that affect the results? Or even if you say like the last letter of Bill is X, the last letter of Gates is Z, the answer is LS.
Yeah.
Like, does that work as well? Not work as well? Not work at all?
Yeah, that's a good question that comes up a lot. So it really depends on the task. I think there's this one paper that said if you did this for math word problems and you sort of had this illogical chain of thought, it would still get almost the same amount of performance, just because for math word problems, the language model has seen so many math word problems in the pre-training corpus that even if what's in the prompt was wrong, could still generate something correct because it was sort of going off of what it had learned in pre-training. I think the answer is like it would depend on the task. And so there are definitely some tasks where if it's like a sort of task that the language model has probably never seen before, then if the chain of thought is wrong, it would probably get it would probably take a big hit in performance.
One more question. So one thing that is not talked a lot, but I just out of curiosity, all the models that we discussed till now, and also this one, what was there uniformity in the decoding method, and does that impact performance in any way? Is there a sense of that?
Yeah, good question. So we use greedy decoding here. Okay. Just for the sake of the demo, I didn't. Well, we use greedy decoding in the paper, and there's this, I think, really underrated trick where if you use like sample degree, like random sampling, you can sample like say, 20 different chain of thought and final answer generations. And this costs more compute, but if you do that and you take a majority vote over the final answers, then you actually get this like pretty surprising increase in performance.
Got it.
I got a similar question. Sorry, not similar, but like it was discussed. Do you know what is the comparison between chain of thought reasoning with explanation-based methods? Like it seems like it's okay. There are differences, but have you compared it to methods that include explanation to come up with the final answer or something like that?
Yeah, that's a good question. I think we have a plot in the paper that shows this. Let me find this real quick. So let me share this tab. And okay, so by explanation, I presume you mean like you say the reasoning after you give the answer. And
Both that as well as maybe it's not in a few shot setup, but your model incorporates that in the training as well.
you mean like when you fine tune?
Right.
Right. So chain of thought prompting doesn't use any fine tuning, which I think is one of the strengths of that. So let me answer the first part. So if you put the reasoning after the answer, which is what some people call explanations, for math word problems at least, you don't see like much performance gain from doing that, and there's still a pretty big delta between doing that and doing chain of thought prompting, which puts the reasoning before the answer. If you do fine tuning, basically like putting the chain of thought before the answer and then doing fine tuning, yeah, I think that works. I don't really recommend that for a couple of reasons. The first is that when you do this fine tuning, you have to collect like this huge label data set of like explanations or like rationales. And that's pretty expensive. The second thing is that like you either like don't take advantage of scale, so you have like a small model that's fine-tuned, or you fine-tune a huge model. But then if you fine-tune a huge model, then you sort of have this single huge like task-specific model, which isn't really desirable. So you can't really you also can't really leverage scale in a nice way if you do fine-tuning. So yeah, that's sort of the trade-off if you do like fine-tuning versus prompting. Does that answer the question?
Yes, thank you.
Sure. So let me move on to some results, and I'll try to wrap up and leave some additional time at the end. So yeah, here are some empirical results for chain of thought. So on the left, we have GSM-AK, which is basically this like grade school level math word problem data set. And then you can see if you do standard prompting in the blue, then you get this sort of slowly increasing performance as you increase model scale. And then chain of thought in the purple star actually outperformed fine-tuned standard.
We cannot see your screen.
Oh, sorry. Yeah, I forgot to switch. Okay, I'll quickly explain again. So on the left, GSM-AK, you have model scale on the x-axis, solve rate on the y-axis, and then standard prompting is the blue dot. It increases slowly, and then chain of thought prompting sort of increases more steeply and beats fine-tuned state-of-the-art at the time. And then we also have another common sense reasoning task called strategy QA. Here the delta is a little bit smaller, and you see pretty good gain just by using standard prompting. But again, we can beat fine-tuned state-of-the-art on this task as well. Let me skip this. I'll just show a quick result here. I think another interesting thing about chain of thought is that it's sort of an emergent ability of scaling. So here we have like 23 different tasks from Big Bench that are particularly challenging. This is a benchmark called Big Bench Hard. We basically look at InstructGPT, Codex, and PaLM models. And again, you can see that chain of thought only has a positive delta if you use a large enough model. And basically what we see in the small models is that either when you do chain of thought, it like doesn't generate anything coherent, or you can't parse the final answer, and that can hurt performance by a lot. Another sort of couple of examples are when you see that there's using standard prompting without chain of thought has this completely random performance. In these two examples, web of lies and multi-step arithmetic, you can see that it's basically totally flat, even for the largest model scale here. If you use chain of thought, you can sort of unlock this emergent performance where you're doing like much better than random by doing chain of thought prompting. I will skip this. Here's this another hand wavy diagram that I like to visualize chain of thought prompting. So the x-axis is sort of the scale of the language model again, and then the y-axis is like the spectrum or range of NLP tasks that you could do with the model. And what this plot says is the sort of blue shaded area is the tasks that are doable with standard prompting. And then the purple or I guess pinkish area is the set of tasks I can do with chain of thought prompting or standard prompting. And the point is that you sort of increase the spectrum of tasks that you can do by using this chain of thought prompting technique. Yeah, the last part I'll talk about is the self-consistency idea that I mentioned earlier. So basically, you use the exact same prompt as chain of thought, except instead of using greedy decoding, so like taking the max probability token at each step, you can do sample decoding. And what you do is you get these different reasoning paths. And then you also get different final answers. And for most of these benchmarks, you actually don't really look at the reasoning path. It's just like something you generate to help you get to the final answer. And so what you can do is you can just say, oh, I only care about the final answers that are generated. And then you can take a majority vote over the final answers that were generated. And we call this self-consistency. The thing that I think is sort of striking about this is that it's this quite simple trick, but you get a pretty large performance delta. So here, note the graph goes from like 0 to 100 on the y-axis, and for GSM-8K, you go from like 65.6 all the way to 74.4 just by using this majority vote self-consistency trick. And in some sense, self-consistency is also this emergent ability, where for small models, because chain of thought doesn't work, you can't save it with self-consistency. And then for large models, you see this pretty big performance delta by using self-consistency. And so for some discussion, chain of thought is sort of this framework for doing more complicated prompting. I think the few shot prompting technique that people previously did was sort of like thinking about analogy, where because we are so used to doing machine learning on XY pairs, we sort of carry that over. But you could think of chain of thought as sort of including metadata in addition to the input output pair. One of the biggest limitations of chain of thought is that it's task specific. So you have to craft these task specific prompts in order to do few shot chain of thought, and that requires the prompt engineer. That being said, I still think this is a huge step up from just a few years ago. If you wanted a language model to do a particular task, you had to collect the data and then train the model. And so like writing these few shot prompts is a sort of a limitation and sometimes a challenge, but it's much more lightweight than what we used to do even a few years ago. And then finally, the thing that really shifted in my mind about language models is like, how quickly language models have solved tasks that previously people did not think were solvable. And what this means to me is that I think it would be wise to be more open-minded about the types of tasks that language models will be able to do in the next, even in the short term, next 1 or 2 years. So yeah, to wrap up, language models acquire these emergent abilities as they get scaled up. The ability for language models to do multi-step reasoning is one emergent ability. And then there are, I think, good reasons to believe that language models will continue to get bigger and better. I'll take 1 more minute to talk about what I'm excited by looking forward. So I think additional scaling is sort of one thing that based on this talk you might conclude is good, and people are doing that, but it's something that only a small subset of like the research community has access to. But I think there's a lot of opportunities in other areas too, like better prompting and characterization of language model abilities. I think we've only reached the tip of the iceberg in terms of the best way to use language models. I think a lot of applied work is going to be really interesting. So for example, I've heard of using language models to like train therapists, for example. And I think that's a really exciting area of how to best apply language models to different tasks. I think benchmarks are something that we also need more work in. So for example, Big Bench was sort of solved in the sense of the language model, the best language model beat the average human rater since in less than a year before since the benchmark was released. So I think we need more challenging and rigorous benchmarks to evaluate language models. And then finally, I think I don't believe the way that we train language models today will be the same way that we do it in 10 or 20 years from now. And I think there's still a lot of room for better algorithms, better optimization procedures, and better architectures that would enable more compute efficient methods for language modeling. I will end here, and feel free to email me with any feedback, and I'll also take any questions in the remaining couple of minutes.
Right. First of all, let's thank Jason for an amazing talk. In the interest of time, I think we have a couple of questions that we can take. So if there's any from the room or from people who joined virtually, let me know. Awesome. Well, so I actually have a question. So you've also found these U-shaped phenomena recently, and could you further elaborate on like why this might be happening?
Yeah, sure. I'll go back to that slide real quick. The reason I think this is happening, I don't think this is like a typical phenomena if you look at like naturally created language tasks. But what I think is happening is that there's often like a misleading subtask that's like hidden in these tasks that are crafted for the inverse scaling challenge. And you see that as the language model gets like slightly better, it sort of starts to do misleading subtasks that decreases performance. But ultimately, if the prompt is like a correct prompt, then as you continue to scale, we would expect that a large enough language model will be able to do that task at human levels.
I see. So you're suggesting that basically because the understanding the problem requires more compute, and then until a certain point, because it continuously cannot understand it, but then after a certain point, it just harms performance. The prompt's hard performance, but then after a certain point, when it's able to accommodate that, then you see this certain spike back up. So that's why you see this usually.
Yeah, like there's this sort of subtask that hurts performance, and medium-sized models can do them. But if you keep scaling, then you can sort of get past that and get the original performance.
Awesome. Well, I think we're out of time, so we definitely want to give Jason a break before the one-on-ones scheduled later on today. So thank you so much.
Thanks for having me. This was fun.
Awesome. See you later.
Bye.